Hello, today we'll be solving problem 4.34. The space between the plates of a parallel plate capacitor is filled with dielectric material whose dielectric constant varies linearly from 1 at the bottom plate at x equals 0 to 2 at the top plate at x equals d. The capacitor is connected to a battery of voltage V. Find all the bound charge and check that the total is 0. So we can see the setup here below, and I'm defining that we have our negative surface charge density on the top plate and our positive surface charge density on the bottom plate. And the first step we're going to want to take is to solve for our displacement vector, which we can do up here using this equation. So we'll do it separately for each of the plates and then combine them. For the top plate, we can define this closed imaginary surface that has an area A on top and A on bottom. And then because our displacement and our area is known and our displacement is unchanging, we can say that d times 2a is going to equal to our charge enclosed, and our charge enclosed here will be our negative charge density free divided times area. And so then our displacement will just be equal to our negative free charge density over 2. Similarly for the bottom plate, we'll do another closed surface with A on top and A on bottom. So then d times 2a is going to be equal to now positive free charge density times A. So then d will be equal to positive free charge density divided by 2. And now if we bring these over to our main diagram here and add them on, we can see that for the top plate, we'll have, it would be coming out if it was positive, but since our displacement is negative, we'll be going in, and it'll be our negative free charge density over 2, and then coming in here. But we already took care of the negative with the change in the direction of the arrow, so that negative should not be there. And then that actually will go all the way to here. And then for our bottom plate, since it's positive, we'll have the vectors coming out. So a free over 2, free charge density over 2. And then again, it extends up to here. And you can pretty easily tell that these on top and on bottom will be canceling, and then the middle, they will add up to have our displacement vector of just the free charge density. So therefore, we can say that, and not free charge density, free surface charge density. So then our displacement vector will be our free surface charge density over 2 plus free charge density over 2, and it's in the positive x hat direction as the way we've defined our axis. So our displacement is our free charge density in the x hat direction, surface charge density. And then because our electric field can be defined as our displacement vector divided by our permittivity, we can say that it is equal to our surface charge density over epsilon in the positive x hat direction. And now our dielectric constant is defined to vary linearly from 1 to 2, but it's linear, so we can set up an equation to basically be able to solve for this dielectric constant. So if we're doing it in the form y equals mx plus b, we can say that our dielectric constant, or our relative permittivity, is going to be ER is equal to our slope times still x in this case plus b. And to solve for our slope, we'll just say our slope is going to be equal to our R2 minus R1, or epsilon R2 minus epsilon R1 divided by x2 minus x1, and that will give us 2 minus 1 over d minus 0, or 1 over d. And that is our slope. And then to solve for our b, we can say ER2 is going to be equal to our slope, which is 1 over d now, times x2 plus b, and solve for b. So now b would be equal to epsilon r2 minus x2 over d. So we'll have 2 minus d over d, which will give us 2 minus 1, which equals 1. So therefore, our dielectric constant, or our relative permittivity, is going to be equal to x over d plus 1. And so now we can, our permittivity is defined as our relative permittivity times our permittivity of free space, and we need that to find our electric field. So we can just plug that in here. So it'll be equal to, as is written here. I'll take the time to write that out. We'll have our epsilon naught times our relative permittivity, x over d plus 1. So then our electric field will be d over epsilon, and, excuse me, we already have that defined up there. It will be our free surface charge density divided by our epsilon, which is epsilon naught times x over d plus 1. And again, in the positive x hat direction. Now to find the bound charge, we're going to need to find our polarization. And our polarization is defined as epsilon naught times our electric susceptibility times our electric field. And our electric susceptibility is going to be equal to our ER, dielectric constant, minus 1. So that's just equal to x over d. So then our polarization will be epsilon naught times x over d times our free surface charge density over epsilon naught d x over d plus 1. But that means we need our free surface charge density. And to do this, we can find our v and then use that, because we have it given, to solve for our free surface charge density. So our potential is going to be equal to negative integral from d to 0 of E, our electric field, dotted with dl. And we can just bring this out and rearrange it. Our free surface charge density over epsilon naught. And I'm going to just switch our limits so that we can get rid of that negative. So instead we'll be going from 0 to d, and we'll have dx over x over d plus 1, so our dl becomes dx, and so we plug everything in, and I will leave it to, we'll want to do our u substitution just to take care of this, so we can let u be equal to x over d plus 1, so then our du will be equal to dx over d. And then just quickly, we can just say, we can bring out our d, du over u will be equal to d ln of u. So therefore our potential will be equal to our free charge density over epsilon naught d ln, plugging back in our x over d plus 1 from 0 to d. And that will give us our surface charge density over epsilon naught d times ln of, we'll have 2 minus ln of 1, because we will plug in these, and that we can rewrite as our free charge density over epsilon naught times d, and then using our log rules, ln of 2. So therefore, our potential is equal to our free charge density over epsilon naught times d ln of 2. So therefore, our surface charge density, our free surface charge density, is going to be equal to v times epsilon naught divided by d times ln of 2. And we can plug that back into our electric field to have v times epsilon naught over d ln of 2, and multiply that by 1 over epsilon naught x over d plus 1, and this is in the x hat direction. So therefore, our polarization will be equal to epsilon naught times x over d times v epsilon naught over d ln 2 times 1 over epsilon naught times x over d plus 1 in the x hat direction. And we can just do some quick simplifying here. And our polarization will be equal to epsilon naught x v over d squared ln 2 x over d plus 1 in the x hat direction. And now we're able to find our bound charges. So for x equals d, our n hat vector will be equal to x hat, positive x hat, and our surface bound charge will be epsilon naught times d v over d squared ln 2 d over d plus 1, x hat dotted with x hat, and that will give us our epsilon naught v over 2d ln of 2. Similarly, for x equals 0, our n hat factor will be equal to negative x hat. So then our bound charge at 0, our surface bound charge density will be epsilon naught times 0 v over d squared ln of 2 times 0 over 2 plus 1, and this pretty obviously x hat times x hat gives us 0. And then our volume bound charge density will be given by this equation, and we can solve that here. So it'll be, we can bring out our constants, negative epsilon naught v over d squared ln 2, and then we'll need to take the partial derivative with respect to x of x over d plus 1, and that's actually it for this because we only have an x component, and that will be epsilon naught v over d squared ln 2 times, here we're using the quotient rule, so low times derivative of high. Our low will be x over d plus 1, derivative of the top will be 1 minus low d high minus high d low. That's how I remember it, over low squared. So now it'll be our top times the derivative of our bottom, 1 over d, all over our bottom squared. 1 plus x over d squared. And then you can see how on the top we can just cancel out we have x over d plus 1 minus x over d. So we can just rewrite this as negative epsilon naught v over d squared ln 2 times 1 over 1 plus x over d squared. Our total bound charge will be given by the volume integral of our surface charge of our volume charge density plus the area integral of our surface charge density, as you can see here. So that can be written out. Our bound charge will be equal to negative epsilon naught v over d squared ln 2, the integral from 0 to d, 1 over 1 plus x over d squared, times our area, and then just dx. So since x is the only component that's changing throughout this integral, we can just pull out our area. And then that'll just be plus, there's nothing changing, no variable for our surface charge density or for our surface charge. So we won't have an integral here. It'll just be epsilon naught v over 2d ln of 2 times our area. And then I'm just going to solve for this part here first to make it a bit neater. So we can let u be equal to 1 plus x over d. So then du equals d over x, dx over d, excuse me. And we did this above, but so then we'll have d times the integral of 1 over u squared du, or something similar above, will be equal to negative d over u. So then our bound charge will be equal to epsilon naught v a over d ln 2. So here I'm just pulling out some more constants, our a and our negatives, and then that will be negative 1 over d times negative d over 1 plus x over d. So we're just plugging back in our u here. And that's from 0 to d, and then just plus 1/2 to take care of that second part here. So that will be equal to epsilon naught v a over d ln 2. And then you can see that it'll just be 1/2 minus 1 plus 1/2, which would give us 1 minus 1, which equals 0. So we've verified that our bound charge is equal to 0. And then just to clarify, and bringing out from our integral up here, our bound charge for our volume bound charge will be negative epsilon naught v a over 2d ln 2, and our surface bound charge will be epsilon naught v a over 2d ln of 2.